Hello and welcome. I'm Lucas, and this is the start of a series about atomically precise manufacturing. Preview. What I'll show you here is that when you make machinery smaller, it will get more productive, why that is, and what that means for macroscale style machinery at the nanoscale. First, we need to talk about scaling laws. When we scale down macroscale style machinery to the nanoscale, we have to check in how far this hurts performance or even feasibility of this idea. But don't forget, it also could benefit performance of this idea. This is a possibility too. Perhaps the most famous scaling law of them all is that finer material has higher surface area. When we go from 1 unit of length to 1/2 unit of length, we go from 1 unit of area to 1/4 unit of area times 8. As when we split the cube, we get 8 subcubes. And that means we get 2 times the area. That is, halving the size doubles the area. For 3 examples, this gives higher catalytic effect of finer powders, the adhesive effect of gecko feet, and the water repulsive effect of lotus leaves. But I won't talk about these because there's already plenty of resources out there about these effects. Unfortunately, the scaling law that finer grained materials have higher surface area also means that smaller machinery has more internal bearing surface area per volume. That means higher waste heat. I will come back to that later. There is a very special scaling law that's very much overlooked, and it's about what happens when you make machinery smaller. That is, when you make machinery smaller, you get, for the same total volume of machinery, more productivity. You get more product per time out of that volume. And that has very, very profound consequences. So let's look at why that is. Why do we get more product out of the same volume when we make machinery smaller? So we see here we have a stack of machinery that successively gets smaller. We have a top production cell, next layer with small machinery, next layer with even smaller machinery, only part is shown, and so on and so forth. As you can see, there's continuity, so there's no point in the whole stack where there needs to be temporary storage. So all that goes in from the lower layer goes out in the upper without any congestions. So the throughput at every layer is exactly the same. But if you look closely, the layers get successively thinner. They get thinner and thinner, but they all have the same throughput. That means that even the thinnest lowermost layer has exactly the same throughput as the uppermost really big cell. And if you would fill the whole volume with the machinery of the lowermost layer, well, then you can imagine what happens. When I say filling up the whole volume with nanomachinery, then I mean this. The gray sheet alone would already provide very practical throughput, and filling up the whole volume Okay, there are some caveats to this. This scaling law only holds for the assembly. There's still the point that the product needs to be transported out of the system once it's finally assembled. And so you can exploit this scaling law only to some degree when the assembly motions are slower than your transport motions. And that is the case if you have a more realistic system where not blocks are assembled with 3x3x3 size, but you assemble, say, blocks with 32x32x32, then the assembly motions are way slower than the transport motions, and you actually can exploit that scaling law quite a bit. Okay, technical detail. In a little more realistic system, where the layers have a stack of equally sized sublayers, blue, you also need transport channels for feeding in the input parts and feeding out the finally assembled parts, product parts. Thus you have high transport speeds and slow assembly speeds. So you go one lane to one fast lane to many slow lanes, one fast lane. So you have the difference in transport motions and assembly motions. So why does this matter? What is this relevant for? Do we really want to fill a huge volume of the smallest machinery? Well, that would lead to exorbitant productivity and exorbitant waste heat. We don't want that. A better approach is to turn it around and look at the other way around. So we have the huge advantage that for practical levels of productivity, we only need a very, very, very thin layer of nanomachinery. And in that very thin layer, there is only a reasonable amount of bearing surface area that causes friction. And also this thin layer is very easy to cool. As I already mentioned, smaller things have higher surface area. This also holds for the nanoscale machinery at the lowermost layer here. But since we only have a very, very thin layer, there's very little volume. So the little volume with the lots of surface area per volume compensates, and we have reasonable levels of friction. If you want to know about quantitative numbers for friction, I took a look, and so far it looks good. I will eventually go into more detail in future videos. Regarding macroscale style machinery at the nanoscale, this scaling law debunks the argument that this won't work because exorbitant friction. There are a lot of other arguments that I still need to cover. One thing I want to make very, very clear is that this concept here is not a proposed system. Absolutely not a proposed system. This is just for the sake of illustrating this scaling law. An actual system would exploit that scaling law, and there are a lot of details to this, which I'll omit here. The scaling law is also the reason why we don't want a soup of free-floating molecular assemblers, but instead a very thin layer of nanomachinery fixed onto a chip, just like outlined in the book Nanosystems. When it comes to an actually proposed system, there are quite some differences. instead of having just single layers, we have layers with stack sizes of different thicknesses. We have robotics vastly differing in character across scales here in blue. We have different connection mechanisms across scales and different nature of part types across different scales in yellow. I may cover all of this in future videos in more detail. Let's briefly look at the mass of the problem. When we go from the uppermost layer, which is here just a single cell, to the lower layers, next layer here, then we might be inclined to think that the speed increases, that these smaller robots move faster than the big one here. But that is actually not true. Actually, these move at exactly the same speed as this one here. Exactly the same distance per time. What's different here is that the length needed to travel is just 1/3. So with the same speed, there are 3 times as many assembly operations per time. Thus, we have 3 times the frequency. So we go from upper layer 1 unit of frequency to next layer down 3 times 3 units of frequency. So we go from, say, F to 3 times F. So we want to show continuity of throughput. That means we want throughput, and throughput is equal to the frequency of operations times the volume that is placed per operation. So what happens with the volume? When we look here, we have what's placed are 3 times 3 times 3 blocks eventually. So we go from 27 times volume to, let's look at the next layer, we have 3 times 3 blocks here. The further subdivision is from the next layer, so don't let that confuse you. So we have 3 times 3 makes 9 times a unit of volume. So now we divide by 27. We go from 1 unit of volume to 1/3 unit of volume. And we put it to when we put it together, we get, if the pen still survives, we get the same amount of throughput, since 3 times the frequency times 1/3 the volume, same throughput. And that's what we wanted to show. You may still ask, why do we stick with the same speed when we go down to smaller machinery? Isn't that arbitrary? No, there's another important scaling law motivating that, which I'll cover in a future video. Still, for an actual system, we want to slow down a bit when going down the convergent assembly levels. Slower speeds of the smallest machinery, of course, means that we need more machinery in the lowest assembly levels. So for each assembly level, for each layer in this animation here, of the smallest layers, we need many sublayers. A single layer in the convergent assembly stack splits up into many of these columns with a stack of assembly cells, transport in, assembly, transport out, and many of these columns in parallel would make just a single layer in the convergent assembly stack. The reduction in speed has twice as big an impact as the increase in the amount of nanomachinery. Thus, paradoxically, we get less friction from more nanomachinery. Going with the speed of the nanorobotics to 1/10 the speed, and going with the number of nanorobotics and the internal bearing surface area to 10x the number of robotics, means in terms of power losses, we go from 1 unit of power to 1/100th unit of power, since this scales quadratically, and 10x the power losses from the increased machinery, and overall we get 1/10 of the power losses. Less friction. Note that we only can increase the amount of nanorobotics due to our all-important scaling law, higher throughput of smaller machinery. For an actual system, there's even more to discuss. When we change the branching factor from 3 to 4, like in this example here, then we still have continuity of throughput. We still have what goes in, goes through, goes out, without any congestions. What does change is that we have lower throughput. The bigger the branching factor, the lower the throughput. The number of parts to assemble, n, equals the branching factor to the power of 3. So when we go from a branching factor to 10x that branching factor, we go from the number of parts to 1000x that number of parts. Thus the major slowdown. But what we gain is more design freedom, because we don't have to plan in so many splits in the product's interfaces. What does not change the throughput is the number of layers. So as we could remove the red box layer or even the blue box layer, we could also add another next layer atop, and all this would not change the overall throughput. It would just change the initial lag time for initial production. So when the whole system is empty and the system starts up, there's a bigger lag time for more layers, but the throughput does not change. It is entirely possible to cut off the uppermost layers of this convergent assembly stack. So we could remove the red layer or even the blue layer or any number of layers, as long as at least some basic nanoscale machinery layers remain. For a topmost layer, the difference is that instead of filling just a product volume inside the build chamber volume, basically the whole build chamber volume needs to be filled just atop. So it's like an extrusion of a solid compact product from below, and that just incurs a constant factor in throughput, in reduced throughput. So in a more realistic system, we would have a higher branching factor, not just 4 like in this example here, but say b equals 32 and say a number of convergent assembly layers of n equals say 4. No more needed, since if we go across 4 layers we get 32 to the power of 4 across scales. So we go about 1 million times up in scale. It's just an approximate here. That means we go from nanometers all the way to millimeters. Also, besides the modification of going with the branching factor to a higher number and going with the nanomachinery slower and compensating with more nanomachinery, there will also be a change of nature in the type of nanomachinery, as at the lowest levels there needs to be mill-style machinery due to very little available space. And at the topmost layer there's the option to go for streaming style assembly, because there's quite a lot of space available. I should mention that in mill-style assembly, transport motions and assembly motions are intermingled as one and the same. They are inseparable, and at every station there's just one assembly step done. So to assemble a block of b to the third, you need a number of b to the third assembly stations along the assembly line, and that makes quite a big long assembly line, meaning the very lowermost layers in the convergent assembly stack are actually quite thick. With that, we somewhat have arrived at a point where we could say we're closing in on an actually proposed system. Huge omissions here, obviously. We haven't talked about a preceding resource preparation layer. We haven't talked about routing layers. We haven't talked about other subsystems. This is really, really scratching the very, very uppermost tip of the iceberg. To bring this to a somewhat funny closure, many possible form factors these devices could take. One of them could be good old smartphone form factor, and advantage of course is they're thin, easily carryable, and if you need the uppermost assembly levels, such a box with a real big robot inside, you could dynamically spawn the uppermost robotics, and you wouldn't do normal robotics that you would expect when you hear robotics. Rather, you could do really cool stuff, really delicate, finger-like, very dexterous things. Yes. Thank you for watching. Like, subscribe, comment, and if you want to support my work, I have information about that in the video description.